So, as an outline, I'm just going to introduce very quickly electronic structure to try to see why it's interesting to use electronic structure for supercomputing or just in any case. Introduce a little bit Monte Carlo simulations in general. And by this, I mean classical type of Monte Carlo simulations. Then the transition to quantum Monte Carlo simulations with its two most common or the most used flavors, the variational Monte Carlo and the diffusion Monte Carlo. We're going to introduce the concept of trial wave function, then how it's applied in a code called QMCPACK that is a collaborative code between multiple institutions, the hybrid concepts, the hybrid parallelization concepts, and how really the computational costs come from. I added a part which is how to target a specific supercomputer to achieve high performance. And finally, when we put all this together, some examples of applications that we can achieve using this type of codes. So electronic structure, basically called also first principle computations or ab initio computations. This type of calculations here basically depend on solving the Schrödinger equations. They are called also ab initio because they are from scratch. Basically, we start from the smallest thing that we have, atoms and electrons, ions and electrons. So it comes to solving the time-dependent Schrödinger equation, which is a partial differential equation, where we have here the evolution of a wave function and the Hamiltonian operator that is applied to the wave function. Generally, solving this equation allows us to solve problems in chemistry, in electronic phases, for superconductivity or magnetism, thermodynamics, optical and transport properties, for plasma physics. All this can be solved with, by solving the Schrödinger equation. Of course, this Schrödinger equation, when we just develop it, it gives us the Hamiltonian operator that we apply on the wave function, have terms of kinetic energy, interactions between electrons, interaction between electrons and ions, kinetic energy for the ions themselves, etc. The most important approximation that we put to be able to solve this equation is the Born-Oppenheimer approximation that is based on the fact that since the mass of the electrons is so much smaller, around 2,100 times smaller than the mass of the proton, we can just separate them into electron from one side and ions from the other side. By doing this, we have two different equations, one that is for the electrons, the other one is for the ions, and then that means that we can take two sets of approximations to solve them, or solve them independently. This is great in itself because this allows us to try to solve it the way we want. Of course, Dirac said, I think in the early 20s, that we can solve exactly this equation the way it is, but it would take us an infinite amount of time to be able to find all the mathematics that go there, and it's just impossible. So we are obliged to take approximations. Depending on the level of approximation that you can take and the specific type of physics that you are trying to reach, there are some things, some type of theories that you can go and try to approximate with. If you want the exact answer with taking no approximation at all, not even the Born-Oppenheimer, you have configuration of interaction, but it's factorial n by scaling, and n is the number of particles that you have. So beyond 10 atoms, you're kind of done. Well, you can do very interesting things with 10 atoms, yeah. So if you go a little bit higher, you have coupled cluster theory, and this one is very, very widely used in quantum chemistry. And it's really great, but the scaling is pretty poor too. The moment you start 50 atoms, 60 atoms, which is the size of nanoclusters. So at this point, it's starting to be interesting, and we're starting to have interesting things. H2O, molecules like this, we can still do them, but the moment we reach larger systems, it doesn't scale anymore. Then you have quantum Monte Carlo that scales between n to the second to n to the third. And actually, in Argonne, this is a little bit outdated, but now we are closer to this point here where we can study very, very, very large systems and we have tricks, etc. And comes the DFT. The DFT theory, which is one density functional theory, is one of the most common theories that is used now. You have codes that are almost legacy codes like VASP, Gaussian, all these codes that are extremely big in the community of solid-state physics and in quantum chemistry. They are widely used. They are great codes. But the problem is that when you see here the scale of accuracy, we are starting to be pretty not accurate. And of course, then we go to tight binding, and this one is absolutely not ab initio method. This one just depends on potentials that are fitted, but we can study way larger systems. So depending on what you're trying to do, you should pick the right theory. If you want to do very large systems, there's no need to try to do this. So this is basically an image of which theory you can do with electronic structure, and it resumes, I think, very well. First principle electronic structure, as we said, it's just solving this equation here. It's great because we only need to put 3 parameters for the input: the number of particles we have, their positions, and their types, the ions. Density functional theory, DFT, which is the most common, is great because it's a mean field cost, so we don't solve for all the electrons in our system, but only for one. Well-developed codes. We have codes that run on almost every cluster in a university in the world. They have VASP, they have Gaussian, etc., and WChem. However, it's hard to improve because they are codes that are so big, so old, and so stuck in whatever they did before that rewriting a 200, 300,000 line code, it's almost impossible. And they don't scale very well. And specifically, the accuracy is basically unknown with the number of approximations that we threw in. Quantum chemistry methods, which are the couple cluster or the CI methods, they are very accurate and robust, but the cost is extremely high, and they are not on HPC at all. Then comes quantum Monte Carlo. It's great because it's not a mean field theory, so we are not bound by the same problems as density functional theory. It's trivially scalable, and we're going to see why. It's n to the second, n to the third. And however, it costs a lot of computer time and human time because the curve of learning is very high and it's a small community. Anyways, all this is to show that each method has good points, bad points. It just depends on what you're trying to do. So I'm just going to talk quickly about Monte Carlo simulations because it may be helpful to see where the scaling comes from in a Monte Carlo in general. So every type of Monte Carlo simulation is by itself a Markov chain or a random walk. This means that each system is going to undergo a phase of transition between a state 1 to a state 2 to a state 3 to a state 4 over time. Also, which is interesting about the Markov chain and to remember is that it's a memoryless type of transition in the sense that you don't need to remember the states that come before, or in other words, the state n+1 depends only on the state n, not the one before or previous. It's like having a drunk person walking in the street. He will just need to know the step he is to make the second step and not the steps before. This is why it's often called a drunkard type of walk. Also, the transition probability between a state from n to n+1 is determined by, it's comprised between 0 and 1. So we need to know that after a long time, we're going to have this evolving according to a master equation for the probability that is going to depend on the transition between n+1 and n1, and the step n+1 and the step n. This means that at the stationary states are actually eigenstates of the probability, eigenfunctions, sorry, of the probability. This is going to introduce another point after the Markov chain, which is ergodicity. Since we are studying physical systems, in physical systems and thermodynamics, it means that the ergodic hypothesis says that over a long period of times, basically all accessible states are going to be equiprobable over time. That means that once you reach a type of equilibrium, moving from one state to another has the exact same probability. That means that over time, we're going to be able to access all these states at a long time. And statistically, with this random process, that means that the time average on 1 second of events is the same as the ensemble average, in the sense that if you do it long enough in a certain region of space, you'll be able to have an average over the whole space. And for a Markov chain, as we saw before, if we increase the steps, there exists a positive probability measure at step n that is independent of probability distribution at the initial step. Basically, this will lead to what we're going to see here for the detailed balance. So the first Metropolis algorithm, Metropolis is the person who first came up with an algorithm to try to reach this concept, is based on 3 concepts. The first one is using the ergodic random walk, in the sense that we're going to be able to screen one region of space long enough to be able to have an average view of the full space. And we need to determine the equilibrium state by using detailed balance. So this detailed balance here is very interesting because when we see how he states it, here, the detailed balance of the probability of transition between a state S to S prime is the detailed balance to go from S prime to S. That means that over time at an equilibrium, we're going to have the same probability from going from S to S prime, then going from S prime to S. And this is, in a sense, what we call a reversible Markov chain. And this is a key concept because we need this ergodicity and we need this rate balance to be able to move along and be able to make sure that we are in that equilibrium phase. If you did not let your system just go long enough, imagine that you're trying to scan a phase space and you have an equilibrium. So first, you're going to just not be in the right place because it's some atypical place that you're scanning, and then you reach that equilibrium. If you're in the equilibrium, that means that you can have all the chances to go back where you were. But if you don't reach it yet, you cannot come back to a state that is absolutely not favorable for your system. So how to add the fact that we cannot go too far or we cannot do something that is not favorable for our system is by adding a rejection method. The general method is we're going to choose a distribution of our samples. Here, usually, we choose a Boltzmann distribution type, or we can choose whatever type of distribution that we want. And we're going to impose the detailed balance transition that will allow us to either go back, if we can go back, or not. And here, basically, it comes back to we can break up this transition probability by adding a transmission and an acceptance, and then we have the optimal acceptance probability that is going to be given by this formula here. So this defines our acceptance rate. So when the second time the classic Metropolis method that was made by Metropolis, Rosenbluth, and Teller were made, then we have, it states that to move from a state S to S prime with a probability of transmission that is constant, and we accept the moves with this. If we repeat this operation many times and given the ergodicity of the system, we will have a canonical distribution of our detailed balance that is depending on the energy of the states that we have. And the convergence is going to be guaranteed, but the rate of acceptance is not. This rate is going to depend primarily on how we're going to sample our system. And I skipped some slides about important sampling, but you can look them up. But in general, for a very simple system here where we have just small balls in a box, you can use this distribution where we generate randomly a number that is going to be comprised between the size of our box here minus whatever function here you want. And we just let our system evolve. So we just going to generate let's say, for example, we take the position of this particle, and we're going to generate a random number that is just going to move it here. So we have, depending on what is generated, we have this small cube here, or we can just generate a particle here, or very far. And this acceptance ratio is the one that is, say, either we accept it or not. Of course, when we have a phase space that is like this, we can choose two types of moving our sample, our particles. Either we move one at a time, or we can just decide to move them all. However, if we move all the particles, the chances that this one will probably get here while all the rest are fine is going to be very high. So what's going to happen is that our acceptance ratio will be very small because we're trying with multiple variables to make them fit within one constraint that we have put, which is our acceptance ratio. Rather than having them one by one moving, we will have more acceptance, and it's better to have more acceptance. That means that you're going to be transitioning faster to where you want to be. So in general, the algorithm for Monte Carlo code, as long as whatever Monte Carlo code is going to be something like this, where we initialize our system, we just compute the energy of our system that we are interested here, and we start looping around it in the sense that we're going to just repeat and repeat and repeat to have this ergodicity system and that to be on an equilibrium phase. We are going to calculate, we're just going to call the samples here. We evaluate, again, the new energy. We find the probability here to go backward to have this reversible Markov chain to make sure that we are past this equilibration time. And then we calculate the new acceptance ratio. If it's accepted, we add it to our variable to the acceptance, to increment on our acceptance, and then we do an average at every time. And we repeat the operation until it's done. One trick to make sure that we have reached that equilibrium is that we can let our system go for a while without refusing any new state and without calling this the probability to go backwards. So we are sure that we are just letting our system evolve and we are accepting everything, and after a while, we're just going to reach that equilibrium.
So what do you do if you don't accept it?
We just reject the move. So basically, we call all the average, and we just compute what we accepted and what we rejected. We keep them, but when you generate a new, let's say we generate a new position, if the position is outside the box that we delimited our space, we say, okay, no. We count, this is one statistic, but not accepted. And when we generate another number. So we can just do this repeatedly, over and over again.
Do you start with a Boltzmann distribution, or you try to reach it with equilibrium?
We start with the Boltzmann distribution because it's more efficient, basically. You can start with other type of distributions, but the Boltzmann distribution is to calculate energies is better. So one good question when we do this type of calculations where it's statistically and we're just computing is it exact? Are we having really the last energy? Are we really having the final energy that we're having? Well, the answer is if we average long enough, technically our errors should go to zero. But of course, it's always the same exact problem. That is, you cannot really never achieve the zero because the zero is only where you put it depending on the accuracy that you're trying to reach. But that means that the errors that we are having are controlled. We know exactly what is the error that we are having. And how accurate is the estimate of the exact value? Well, the simulations come with an error bar. If we put a result of any energy that we computed from a Monte Carlo simulation without an error bar, we don't know really if it has any significance or not. So we should always understand what we are doing when we do this type of calculations, and we use a lot of ways to be able to compute this error bar. Most of the time we use the central limit theorem. We can do averages using statistical process or normal Gaussian distribution, and the error bars are usually the square root of the variance, So when we plot at that time the trace of our simulation, and we have the energies here from our simulation, we can see that this part here looks like an equilibration time, and then after a while we see here the distribution, and if you plot the histogram of E, of the energy, we see that it's really normal distribution. That means that our statistics is good. Okay, so now that we have an idea how we can do this with the classical Monte Carlo, what's the difference with the quantum Monte Carlo? Well, we need quantum Monte Carlo when we use it to solve the first equation of the Schrödinger equation. We need to be able to solve the many-body quantum problem as we just saw that in the classical way. When we apply the Hamiltonian, we need to have the wave function and the expectation values are determined by the simulation. That means that everything that is intrinsic to the system is carried by the wave function that is the key of our problem. Most of the quantum Monte Carlo simulations are interesting for scientific purposes because the correlations between electrons are carried in quantum Monte Carlo theory, and it's not in other type of theories. It's based on Feynman's imaginary time path integral. So when we're gonna make a system evolve, we're just gonna use the imaginary time and not really let the system evolve in the real time. QMC is great because it gives us very good accuracy, like I showed earlier. There are ways to use quantum Monte Carlo beyond the static system or beyond. We can use it to evolve the system at high temperatures with path integral methods. And we have a variety of quantum Monte Carlo that we can use, such as VMC, variational, projected methods, path integral, and etc. Here we're just going to focus on the variational Monte Carlo and the diffusion Monte Carlo. So basically, the variational Monte Carlo depends on the variational principle, which, like any variational principle, allows us to bound our wave function with a max and a min. If we start with an appropriate trial wave function as a start guess for our Monte Carlo simulation, the trial wave function needs to present very few constraints. It has to be continuous, which is for a physical system quite normal. It has to have the proper symmetry, normalizable, and finite variance. So in quantum chemistry, we usually use a product of single particle functions, and we're going to see a little bit later how this goes. But we need for Monte Carlo, we can use a computable function, either a sample of the density of our wave function using a Markov chain Monte Carlo. We can take the average of the local energy and we can optimize the wave function, the starting wave function, until we get the best upper bound that we need. And usually the error that comes with it is second order. So with a better wave function, we have a very low variance. So it becomes a very, very difficult task to be able to detect what is the good starting point for any Monte Carlo situation, a quantum Monte Carlo, or in general for a Monte Carlo. What is the initial guess that we start with to be able to start our experiment? For the variational Monte Carlo code, the algorithm is also more or less the same as the other one. It's just that here we have to, when we sample, the positions are based on the density of the wave function. And we're just going to find the transition probability exactly like we did for a normal Monte Carlo. And then we're just going to accept the probability, or if we accept it, we compute the acceptance rate. If we accept it, we just increment our counter. If we don't, we just reject the move and we do the averages. In the case of the diffusion Monte Carlo, it's a special case of the projector type of Monte Carlo, where we're going to let a state evolve in an imaginary time. This allows us here to, I'm just going to do this one. So this allows us here to be able to get rid of the bounds of the wave function. In the variational method, we have, because of the variational principle, we are bound by the wave function. When we let the wave function evolve, we don't have those bounds anymore, and we can reach an absolute energy. So we have a projector here, and we're just going to expand it to the exact eigenstates of our Hamiltonian. And then we're going to have our wave function here that is going to be the wave function is going to evolve simply with a basis set that is based on the evolution. And at long time, the limit is the lowest energy state that overlaps with the initial state, usually the ground states. So that means that once we let our system just go longer and just diffuse longer, we're going to be able to reach the absolute minimum, of course, as long as we are sure that our system just had time to converge slowly.
Maybe you missed that one, but what is capital R in terms of notation?
Oh, sorry. The capital R here is the positions, the space and imaginary time. So it's based on the importance sampling. How are we going to sample our trial wave function? So in statistics, the importance sampling is a general technique for estimating properties of a particular distribution, while only having samples generated from a different distribution rather than the distribution of interest. This means that basically, when we do not know the distribution that interests us, we can start from a distribution that looks more or less like it, and then we let it evolve slowly. So in statistics, it's also related to, people call it umbrella sampling, or there are multiple methods in statistics that just relate to the importance sampling. So once we have this importance sampling, so in general, for physical systems that interest us, we try to find the correct answer for the partial differential equation, which is the density here, the density or the square of the wave function. But of course, we don't know that answer. So we have here, when we just break it here by a trial wave function, and we just have the evolution of our system here over time, we can see that this evolution is going to be a diffusion, a drift, and a branching. And we're going to use the accept and reject system that we said before. When you generate a new configuration, you need to let the system evolve. If you accept the move, you accept it. Otherwise, you refuse it. But here we have a second term that appears, which is the branching. Schematically, that means that once you have a configuration here, you will have three options that are going to appear. Either you're going to be able to, when you generate a new configuration, you will be able either to diffuse it or having a drift, or some of this configuration will not be accepted because they are not statistically viable, so they're just going to die. Others are just going to diffuse, so first configuration accepted, it diffuses. Others are going to branch. They are so favorable because here, each one of them have a multiplicity. They will just give you 2, etc. So one of the important things that happens with this type of schematics when you have diffusion type of Monte Carlos is that, of course, you can have first ensembles. So ensembles means that because of the ergodicity of the system, you need to be able to scan long enough a region of space to be able to have all the information about the whole system. That means that basically, this means that you can just reproduce your system to an infinite amount of systems and let them do the work for you. So if you have just one system, you can just do the operation for a very long time, extremely long time, and then you'll be sure that you have just visited all the spaces. Or you can just clone your system, your initial system, and then let them evolve for a shorter time, and then you will be sure that you have just seen all the systems. In computationally, this means that you can just reproduce and clone your system over multiple nodes or over multiple systems, and you will be able to have your solution in a faster pace. However, because of this branching, that means that if you start with, let's say you have one ensemble per node, and it drifts, that's fine. You still have one ensemble per node. But if you have branching, some nodes will end up with one one ensemble. Other nodes will end up with 2, 3, 4, etc. So you need to be careful with the load balance that you're going to have. So again, the algorithm for the diffusion Monte Carlo, we have the same type of things where we initialize our states. We're going to evaluate the trial wave function. We're going to evaluate the drifts that we have. And then we're just going to apply everything that we saw, which is we're going to generate a new trial wave function. We're going to add the weight for it to see if it's going to be viable or not. And then we're just going to repeat the operation to see if we're going to have drift, if we're going to have branching, or if we're going to have diffusion. All the weights here are, each move that we make is weighted, and then we're just going to reweight everything, average, and accept or refuse or reject the moves. So I talked about trial wave function, but how complicated is it to find a trial wave function when we don't know the system that we're trying to solve? Well, there are some requirements. So the formal requirement is that we need, because it's a physical system and it's a wave function, we need the antisymmetric properties. It needs to be finite. We need continuity. And for mean field type of approaches, like density functional theory, we use usually a Slater determinant. We can also use expanded space by using multi-determinant or even configuration of interaction. And there is the local energy argument, which means that we need to control all singularities close to at close distances between electrons, and that in the sense that you cannot have two electrons that are just going to be on top of each other. Of course, you need this type of spacing between them. We have the behavior at large distances. That means that our wave function needs to be able to cover very short and very long distances, because van der Waals type of forces or plasmons are all depending on this large type of interactions. And we have the Feynman-Cox formula that gives us connection to local energy. And we can do that by using Jastrow's backflow three-body, and I'm going to it. In more practical ways, to try to find our trial wave function that we've been talking about so much, we usually need to start from something that we know, and that something that we know is the asymmetrical function that comes from the Pauli principle. This asymmetrical function here basically comes from another type of calculations. We can start with the DFT calculation, for instance, or any quantum chemistry method, and we try to complete it with this type of term here, which we call a Jastrow term, that is going to give us, this comes from, so this asymmetrical function comes from a mean field theory. So that means that one electron sees a field that is surrounding it, not each individual electrons. Quantum Monte Carlo tries to solve exactly all the interactions between all the electrons. So basically, we need to be able to reproduce what we lost between the interactions. And this is why we use this Jastrow function here that gives us the interaction between each electron and its neighbors. So we can use a one body, the second neighbors, and all the interactions. And we can go just with this development to as many as we want. So the most common source for the single particle orbitals that are part of the trial wave function come from a DFT code, as I said. Usually these wave functions are represented by a plane wave basis, like this here. And each single particle move, so each time we decide to make a move, it requires the evaluation of every orbital for the new position. So this means that for every move, we need to redo the n-plane wave calculation evaluation for every orbital, which can be very heavy. So the first thing that most of people, or actually almost everyone does, is not to use plane waves. So plane waves are completely inefficient. And even if you are not doing quantum chemistry or you're doing anything else, and you have some type of input that is like this, This is fine to use this when you have small clusters, but on very large systems, this is very inefficient to evaluate because you have this exponential here and it's going to be extremely costly. So rather than to do this, we use a real space basis. So rather than having the real space basis, we use B-splines because they are a very good choice and they are very efficient. And there are many papers that describe how B-splines are extremely efficient for all scales of computers. And for each basis, we can, for each point, we can have only 64 basis elements. So that means that for each point that you try to evaluate in space, you can imagine a cube around it that can be represented by 64 points. So rather than having to evaluate a full function, you actually just evaluate 64 points, which is really fast compared to having to do the exponential with the vector multiplications, etc. So there are many functions that exist that are able to do this evaluation of the B-splines. One of the libraries that we use is called Einspline. Other codes use their own homemade libraries. There are blibs. So it's fairly easy to be able to do this interpretation if you have this type of plane wave type of calculations to just go to real space and use B-splines. This is what we used in the code Quantum QMCPACK. The code has multiple contributors from multiple national labs and the University of Illinois, and some people who went to private companies. So QMCPACK is, I chose QMCPACK because I'm one of the developers, so it's easier for me to talk about it rather than another code, but there are also other codes that are extremely good. There is the Casino code by the Cambridge group. There is QWalk that is also by University of Illinois at Urbana-Champaign by Lucas Wagner, which is a great code too. They all use more or less the same things. Here, so QMCPACK works on common supercomputers, GPUs, not GPUs, in BlueGeneQ. It is C++ heavily templated code with object-oriented, so it gives a lot of flexibility to any newcomer to be able to contribute to the code. It has MPI, of course, it has OpenMP, and it has a GPU CUDA for some parts of the code. The way we try to write it is that the inputs are in XML, so it's very easy to move from one code to the other. Since, as I said, the important part for our trial wave function is to start from something generated from a lower type of theory like DFT for our trial asymmetrical function, and then we correct it by a part by this Jastrow function. That means that we need to grab the output from another code. So having the XML input and HDF5 type of, are you familiar with HDF5? So having HDF5 allows us to do cross-platforms, moving data from cross-platforms, and I can assure you that this is a lifesaver. Because when you have an Intel machine, for example, writing you in a binary file and you need to move it to any other system, you can't. So HDF5 is a good option. So now, how do these B-splines that I just described, that basically are our wave function completely, do with the memory? Well, in QMCPACK, we use a regularly spaced grid of points to calculate the 3D B-splines. So this grid is the 64 points that I gave you. We're just going to put them over a mesh that we can control by ourselves according to the precision that we are trying to reach in our system. It's extremely efficient to look up in the memory and streaming from any wave function to the CPU. So basically, whenever you do a move, a random move that is generated, we need to go and reach and access a part of the memory randomly because that move has been decided randomly. So we need to be able to access the memory to the CPU quite fast. It's inefficient in terms of total memory used. Why is that? Because even if all the wave function may be small in some region of space, we need, at some point, it's going to be very large because if we need vacuum in our system, let's imagine you're trying to describe a nanocluster in a huge box. You will have a lot of information around your material, but the vacuum is still there, and you need to consider it, and it's going to take space. So it's not completely, it doesn't use very efficiently the memory. The wave function are going to typically vary very rapidly around the nuclei. So the more we get close to the nuclei, the more. If you imagine it as in terms of a sparse matrix, you're going to have very cores close to the nuclei, which is going to just make it very heavy to compute. And so there's the hybrid parallelism that we use is relatively simple in the sense that we're going to have to move a given walker. Each given walker, when it moves, is evaluated by a single CPU. So if you remember, we said that we have these ensembles. So each one of them has to be just evaluated by one CPU at a time. So every core has to be able to access quickly to the wave function and to evaluate all the single particles at that point of space. So this is great because all the modern supercomputers, we have tens and hundreds of cores per node. So that means that all these nodes will need to access the same wave function very quickly. The single particle wave function are never changed during the calculation. So the single particle doesn't change. It's usually the coefficients of our B-splines that are recalculated and reevaluated. So when you have this situation where you have multiple cores having to access same memory, each one of them doing the independent part, that is great because we can just share them between all the cores on a node. Each wave function is going to sit on a node. Each core is going to do his job or its job on the part that is interesting to him for its walker, and we're going to just be able to share that memory. The bad part is that, well, if the memory does not sit on one node, the calculations become too big to be able to be executed. So we can use also, QMCPACK uses a combination of MPI and OpenMP for parallelization, and you can replace that OpenMP with CUDA. OpenMP on a node makes sharing large static data for the wave function very easy. So there are many parts where each core needs the same information. It can be shared. It can be the work can be just split between all the cores on a node for a simple reason is that they only require the information that is sitting on the same node. If we look a little bit at the schematic of QMCPACK, so we had the QMC driver that is basically whatever type of calculation you want to do, VMC, DMC. You have each ensemble that is considered by an MPI group. And here, I think this is like very descriptive of what type of Monte Carlo you can do. You can do all your work in only one ensemble and let it go for a very long time because of that ergodic principle that you need to be able to scan long enough to have all the systems. Or you can just share it, and each one of your ensembles will do one or two moves. So this is how you can just achieve that perfect parallelism between them, because the more you increase the system of the number of your ensembles, and the faster you will get your answer. So it's really that linear. So we have one ensemble here. Each ensemble can have an MPI task, and you just split the walkers per. Here, it could be either an OpenMP process or a CUDA process. So same thing here. If we go inside the population of the walkers, we will have a population here, either with drift or branch or just transition. And this is going to go further. In terms of making a move here, we have the drift part that is here with the accept or reject move. And it's going to be weighted with the local energy. And we can collect the information and do the load balance. So here is the main So here is the main problem that may happen in any type of drift type of quantum Monte Carlo is that you can end up with a population that is more or less fixed and having increased population on some of your nodes and other nodes who have not enough work to do. So you will have this communication unbalance and load unbalance. And there are ways now that you can find in literature how to do a smart type of load balancing by just fixing an upper bound and a lower bound in the number of ensembles that can be created. And you can just fix this problem by just decreasing the communication between your nodes. So basically, so far for quantum Monte Carlo, it's a simple, even if it did not sound that simple, way to do QMC. So far, having the MPI plus either OpenMP or CUDA gave us really good solutions to be able to do abstraction of the physics concepts. It's extensible and efficient in the sense that we can always increase the number of ensembles that we have, and it will always almost linearly reduce the time to solution. It's object, in our case, it's object-oriented, so it's very easy for new coders to just arrive and add functions without having to know exactly what is behind the classes. It's efficient in the memory use as long as we have enough memory. It's portable and scalable. We have it even on Mac laptops. This is to say how easy it is to install the code. And of course, it's very optimal when we use extremely large supercomputers. In terms of performance on BlueGeneQ, I guess you already seen this slide. But OK, I'll just back up. So I am aware that the full theory behind it is not as simple, and it's a lot of things to just put in a very small amount of slides. But basically, it's a nice theory that works to solve many things, and I said it's very scalable, and it's great. However, it's not as great as it is because now with the size of the supercomputers that we have and the systems that we have that are so targeted, you can have a machine like Titan that has many GPUs and just a few CPUs. You have machines like Mira that has OpenMP with threads and many threads per node. You can run multiple tasks. It's not enough that your code scales well or that your code is great on your laptop or even on your university cluster. You need now to target your code for the supercomputer you're going to be running to be able to make the exact modification in your code to take advantage of these machines. But there's also another thing is that it has some high performance features. And these are built-in tools within any supercomputer that you're going to find that technically allow you to do mathematical operations faster. Here, for instance, on BlueGeneQ, we had the quad FPU, so we can use QPX. That means that we can have 4 operations, 4 doubles at the same time. We can have 4 wide double precision FPUs. We have usable as scalar FPUs. We can have 8 concurrent floating point operations, FMA plus load and stores. All these are operations that sound, oh, I will never use this, or the compiler is going to do this, but most of the time, it's not the case. So for QMCPACK, we just took whatever was available here, and we tried to see how we can improve our code. And it was quite interesting to see what we did. So we took a generic system which is an argon type of solid. Argon is a noble gas and also a national lab, but this one is the noble gas that we took. So it's a fairly large system, just to be able to see, and a typical type of system that we've seen. We have a wave function that its size is 1.9 gigabyte, and as I said, the wave function has to sit on a node. A node on BlueGeneQ is 16 gigabytes, so we're fine. So we know that we have access to the memory. We use 32 threads, 1 MPI tasks, and 2 walker per thread. So each thread has 2 walkers. And we started profiling the code. So as I said, the code it's based on a Monte Carlo. That means that it's extremely scalable. So it should have been fine. But here we did a type of profiling, we saw that we are very balanced between arithmetic and floating point operation. We have an LD1 cache of, we hit at 94%. We're supposed to be OK. I mean, this looks really good the way it is. We have a percentage of peak that is not great, but it is what it is, and a total runtime in 53 minutes. So the interesting part of this is when we do just a gprof, a normal gprof, just to try to see where our time is spent, we realize that the evaluation of the B-splines, so every time we make a move and we have to evaluate the wave function within the 64 points that describe every one of our points in space, well, this is where all our time is spent. Basically, we have almost 70% between these two functions that are for the evaluation of the splines. OK. What can we do? So here I'm just going to fly through these slides because it's not that much. But basically, when you open this, I said for each orbital that we have in a system, we need to evaluate 64 points around the point that interests us for all the points. It comes to this first loop, second loop, third loop in space. If you imagine a cube, x, y, z, 4 points for each one of them. And here, we just loop again around our orbitals. OK. And we do all this operation one after the other. This is an initial code that is written by a physicist who sees the equations and just applies them. It's great, but how can we do? The classic techniques, and there is no secret in here. You do you just move your loops by reordering your loops. You unroll some loops. You see if you can do some arithmetic changes in your program, and you see if your data loads that you're having are good enough. So in a magical world where compilers are great and do their job, you don't need to do this type of things. You write whatever you want, and the compiler just thinks and finds you the best way to do it. But then if that compiler does it, it will also take your credit card and just evolve and put you into slavery. But that's another. So what we can do is to change the type you write your equations. And basically, by just reordering some things, you can see that you can start looking at seeing patterns in the way we were writing things. So first of all, a lot of people use complex, the keyword complex. It's great, but it's a waste of time. It's basically declaring two variables between the real part and the imaginary part will save you time. This is what we did here. Basically, we just rewrote mathematically what we did, and we started seeing these patterns. OK, all these are close memory, close packed memory, close to each other. And we just started removing things slowly and grouping them. And the thing is that what the compiler had to do when you have one vector like this multiplied, it's a matrix basically. When we have matrices like this, is that machines give you the opportunity to have these very fast function calls that allow you to do the same operation for a lower cost. In the case of BougeQ, it's this vector load, or you have vector splat. So rather than calling this 4 times, it's the same variable. You just put it in one, and it costs you less, and it's already in the memory, and it's great. So this is writing with intrinsics. And this here, by doing this type of operations, by loading this whole memory at the same time and putting it in only one value, will allow you to save time. So we did that like more and more with the help of the performance engineers and Hal Finkel, who was there. We spent a lot of time doing this. And at the end, we end up having all these operations that I showed before in 2 or 3 lines like this, very nicely with just specific operations that are related to the IBM. They exist also. We did it for Intel compilers and for other platforms. And we did, again, the profiling. So we went from a number of cycles of 1.8 million to 200,000. Basically, we reduced the speed by we increased the speed by 7.62 times for this function, which, when you think about it, is just we reduced the number of computations that we did, because then our program is not as much balanced. Our peak rate decreased, so we're doing less, and our hits on the memory are lower. But we don't care as much because the purpose is really to have a speed up in our program and to reach the result faster. So for the same system that used to run in 53 minutes, now we run it in 20 minutes for a total time speed up in the code of 2.68 times. So this is what your compiler should have done, and that was not done. So really, the point of all this part of the code is to say, if you have your code that is great, and even if it's greatly written, try to do some performance profiling on it on the machine that you're going to be running, because sometimes you need to do some specific work on it to make it go faster. When we did all these modifications and we test it on machine, we test the whole code on machines like Mira and Titan. For QMCPACK, we see that we have a perfect scaling for both machines, Titan and well, for Mira, and actually this one was made on Sequoia. So we can scale up to almost 100,000 nodes, I think. No, cores. Sorry, yeah, cores. So basically, this represents almost a full machine. We are almost linear up to 95%. On Titan, with the GPUs, there is some type of, here we reach our limit that is basically due to the fact that when you try to do this evaluation of the splines and send it to the GPU to do the computation, at some point you hit some communication barrier. So this is why it's not that linear when you reach a very large type of systems. But just with CPUs, it's also completely linear. Applications. So I'm just going to go very quickly through them. So basically, with codes like QMC, we can do multi-determinant type of wave function to be able to estimate the exact energies and the correlation that we are computing for light elements. We can do benchmarking for molecules where we're testing against other type of either couple clustered, which is one of the most precise, to see exactly how good we are doing compared to them. We can do properties of metallic covalent and van der Waals solids using standard recipe. Well, this means that we're doing it with a one single Slater determinant. And here, basically, what we have is how good we have the values for the energies of all common solids. That means that, for example, aluminum, we have the exact energies for cohesive energies, lattice parameters, bulk modulus, all these things, we can compute them more or less to a very, very good accuracy. Here we have also, we did the same thing for rare gas elements, argon, xenon, krypton, and we have very, very close to the experimental values. We also did the same thing with big biological molecules. And again, there are multiple applications using QMC that you can find that have very, very broad type of applications. This is here for the exact exchange, computing the exchange constant in the cup rates. So really the application can go from material science to semiconductors to batteries to biology. So it's really one of the most interesting fields now because it's very well, it gives us a very good accuracy, and we can scale over the whole systems like Blue Gene or Sequoia or this type of machines. So it's really very much used. Challenges, well, we still have to do a little bit better in the efficiency that we are having. The balance for memory versus computational intensity is also important. At this point, we do a lot of loads, and we have to seek for the information multiple times, actually, for each random query that we do. We have to expose more parallelism, and we are actually working in doing nested threading. And of course, there is the handle defaults. If any node on our system decides to die on an application that lasts 10 hours, well, we're kind of done because the whole statistic is going to crash and we cannot recover from the death of one node. But this is an MPI type of problems. Yeah. I like to acknowledge all the people who gave me slides and who helped me with this, and Argonne, and also the BES project. Do you have any questions? Yes.
So I was wondering, so rewriting some of those loops can be a lot of work.
Yes.
Did you use a profiler to maybe hit your high priority loops, or?
So we started with profiler was. Oh, so did you hear the question? Is to rewrite the loops that we did we use a profiler? Well, basically we started with gprof, and we were surprised to see those percentages. Then we worked a lot with HPM to be able to have really the number of flops and the number of cycles. But at the time that we started doing that, not many profilers were able to handle OpenMP, which is not the case anymore now. They're doing way better. But yes, so gprof, we started with simplest ways. gprof, HPM is a good start.
Did you have to update basically all of them, or a smaller subset was made a lot?
No, so you cannot decide to optimize every part of your code because it's inefficient. So basically, when you're lucky enough, like we were, to have 70% of our time spent in two specific functions, you can just go and see which one they are. Now that we are back to 14%, 15%, and the next function is 10, and the next function is 10, then you need to choose the one that you think is going to be the most easier to do, that is not going to take too much time, because if it takes you 2 years to optimize it to gain 2% on it, it's not worth it.